So far we just looked at the two-stage amplifier. We will see that now we will see the three-stage amplifier. This is let's just start from the first stage amp. In this amp we have a output pole. So in the body plot we have the only dominant pole at the output. So what we care about is this GBW FU. That is what GM1 over 2 pi CC, because all the current generated from this V-in variation, that is flow through that, the capacitance, that is what the GM and V-in current, right? So the voltage V-out minus GM V-in times 1 over SC. So the gain AV equal to 1 lead us the FU equal to what? GN, like that, right? So for stability analysis, and this DC gain is not that important. So whether if the RO is the RO of the M1 is large, then you get the larger DC gain. If the RO is small, then you get the lower DC gain. But for the in terms of this first dominant pole only give us the phase shift of the 90 degree at most. So for the stability, it doesn't matter. So we can say that the one-stage amplifier is inherently stable if that is used in the any feedback, right? So we feedback, if you put a feedback like a resistor feedback, whatever, right? Minus there, it is all the stable, right? Right. Now if you add this another stage, then you have a two poles node. Without CC you get the 1 and 2, right? P1, the F1 and F2 are closely spaced, so that results in the 180 degree phase shift. So by adding CC after CC, then we split this F1 and F2. So FU is defined by GM1 over 2 pi CC, right? FU, and F2 is what? The GM in F2. So the output pole location. So CC here at high frequency, mid-band frequency, the impedance is small, and also the input impedance into gate is infinity, then the no current, right? Zero voltage drop. So it looks like a short connection. So we have, right, and CL, right? So 1 over GM is the R equivalent. So the pole location becomes GM2 over 2 pi CL. This is something that we already we know that, we have learned that. Now the question is, if we add one more stage, then what happens? If you recall the two-stage amplifier compensation, the first stage is positive GM and second stage is the negative GM, right? The negative GM is required for Miller compensation, right? So that the voltage gain from input to output is the negative gain, right? Here to here is negative voltage gain. So that can be applied to the three-stage amplifier. You can view that this second stage amplifier is additional two-stage, let's say two-stage amplifier, but it has the negative voltage gain, so minus GM there, right? Because this is a two-stage amplifier, it requires additional compensation capacitance. So look at this, the three stage, this is the positive GM. The second stage is positive GM, right? Positive GM, positive GM. But the last stage is negative GM. So the overall, this second stage is what? Minus GM, right? So 1, 2, 3. 1, 2 times GM3, right? So you can see that the second stage amplifier need to positive voltage gain, right? So the second stage be positive gain amplifier. Right? So because the GM here, if you write GM, typically for the GM we draw like in this symbol. So if you take any load RO here, for the input variation V in, the output current is proportional to input variation. So the voltage will be what? V out equal GM times RO times V in, right? So this is positive GM, a positive gain, right? So for the ideal transconductance, for ideal, let's say, for an ideal transconductance amplifier, right? What would be the characteristic of the output resistance? And so the what? The RO is infinity, and so thus the AV is infinity. Okay. So if you add one more stage, we get this additional pole introduced. So you can think of, so when you compensate this three-stage pole, so you have a 1, 2, 3, right? So F1 and F2, F3, right? That is after CC and CD, there are two compensating capacitance required. So we would like to make that 1, 2, 3, right? So the same thing happens. So F1 and FU here, F2 and F3. So all the non-diagonal pole, we wanna move that F2 and F3 greater than FU. That's something that what we want to have. So you can think of the second and third stage as the single amplifier, right? So then, if this second and third amplifier is fast enough, if it has a large bandwidth, then it behaves like a two-pole system, right? The two-stage like a two-stage amplifier. Now inside this amplifier, we have two two-stage amplifier. So in that amp, we add additional compensation capacitance, right, to make it more the ideal. So overall GBW is the same, GM1 V in GM1 times V in current will flow through the CC compensation capacitance, and then output voltage is determined, right? Because the second and third gain is large enough, we can assume that this node is AC ground, right? So if that is the case, at midband output voltage is what? minus GM1 V in times 1 over SVC. Based on that, we can find that GBW, right? Same as like that. And the non-dominant pole, location of the non-dominant pole. We have two non-dominant pole, first and second non-dominant pole. The first non-dominant pole is GM2 over CD, right? Capacitance seen in here. So at that node we have a non-dominant pole there, and the output side, another non-dominant pole, that would be GM3 over 2 pi CL. So we want to design that first non-dominant pole 3 times FU, so that we want to design 3 times FU, and then another third pole, the second non-dominant pole, we want to place that around 5 times GBW FU. Yeah, then it looks like a behave up until FU. It looks like we keep the one pole roll off, right? Minus 20 dB per decade. In this way, we can have a stable amplifier inside the feedback. Okay. So far our discussion was based on the assumption of beta equal to 1, so the loop gain is the A beta and close to at A, right? Because the beta equal to 1 is the most the toughest, the worst case of the phase margin. So when we analyze this amplifier stability, we assume that beta is 1 case. Okay, that's why we plot this amplifier open loop gain and then analyze the location of the pole and location of the pole and zeros. Okay. This is an example of how we actually implement a non-inverting stage as a second stage. Let's start with the differential pair here. If you tie the positive terminal to the input and the other negative input to ground, then the gain from input to output here is the positive, right? So if you change the current here, if you change the voltage at the input, they will increase the current like this. That will be what? V, let's say this is V in. So V in times GM. This is V in time. No. If you change this voltage, then we will have a change in current, right? Current, ID. The same current will flow through to the output, right? Like this. This is a differential current, right? So that will this output current will see the output equivalent R out resistance, and so that will bring up to what the ID times R out, right? Voltage gain. This is the V out. So gain from here to output is positive gain, right? So, but in this case, the output range and input range are limited because for the minimum, let's say minimum input voltage, min input V in, is what? So this current source require what? VD set, right? Plus, right, VGS here, VGS. So minimum voltage for the input must be greater than VD set of the current source on the bottom and the VGS of the input pair. But for the output, so V out what is the max? Let's say for the maximum, what is the maximum V in? It can go up to what? Up to VDD, right? If you go up to VDD, it is like still in saturation because the drain is at the VDD. So for the output, let's say minimum output is what? Mean V out must be output must be greater than what? Here same. But in this case, what V in, if the once the V in is tied to common mode level, let's say VCM. This is the AC ground. This is the AC ground. Right? So if the output is tied to VCM, then the lowest it must be what? V greater than VCM minus VTH, right? This one minus VTH, so that the input pair on the right is in saturation, right? So that is limited by the input common mode level. And for the maximum, let's say maximum V out, it can go up to where? It should be below the VDD minus VD set of the IB current source, right? This current source also require a VD set drop, right? That is let's say that is what? Okay. So that is limited output range and input range. To even increase the range, input and output range, we eliminate the tail current source, so that we can have just current meter structure like this. So we have input coming in, input goes up, the current flow, this current metered onto the output. So any output resistance there, equivalent resistance, the current flows through the resistance. It shows that positive voltage gain, right? But in this case, it goes through the PMOS. PMOS device require typically 2x size, right? 2x size for same GM and the what we have to look at for the sizing is GM and what V overdrive, right? So this overdrive voltage is equal to what? VD set, right? That actually limit the range, set the range of the output, right? So this VSG should be VTH plus V overdrive, right? So this overdrive voltage is VD set of this transistor, right? So that actually affect the output maximum voltage. So PMOS, since PMOS for the same GM and V out, it has the 2x size, assuming what? Mu n, if the mu n mobility of the MOS electron is larger, right? Approximately 2 times larger. So in some case, this leads to what? Low bandwidth. Low bandwidth. You may use a different topology, like using MOS only structure. So by folding this current mirror using like this MOS style, instead you are adding more current, like 2x current here. So if you change the voltage here, current flows like this, right? This current need to flow from here, right? I'm sorry, flow through drain and source like this, right? This current will replicate it like that. So any output equivalent resistance there, this current will flow to output, right? So it gets the positive voltage gain. So this is the MOS only, so typically it has a smaller size than the PMOS device, so it leads to higher bandwidth. But the penalty is you are using what? Here 2 IB instead of here is IB on the left hand side. You had the IB and IB, so total 2 IB. So 2 IB current consumption, but here 2 IB plus IB, so 3 IB total currents are required. So more current, more power consumption there. But in some case, if you want higher bandwidth, you may try this. Okay. So it depends on whether you want to focus on more on speed or power. Depends on the requirement. You may choose one of those methodology. Okay. This summarizes all the equations for the 3-stage amplifiers using nested Miller compensation. Typical design is like GM1 is smallest, and as you go from the left to the right, the GM getting larger and larger. This is because what we have to do eventually is that the dominant pole in here and second and third. So here is dominant pole F1, and then what you have to do, what's important, FU and F1 and F2, F2 and F3. What you have to do is the FU must be low F2 and F3. But what determine FU and F2 and F3? FU here, GM over C is CM1. That is what FU 2 pi FU, right? So FW1 omega 1 is what determined by GM2 over CM2, and WF this is the F2. So in this notation, this is F2. So G 2 pi F2, and this is the 2 pi F3. So as you can see, considering the similar for similar capacitance for CM, so this is called CM2 and CLs are comparable. For if the CM, C2, CLs are comparable size, then the GM should be designed in that way, as I showed you before, right? So if you look at more carefully that we have 3 poles here, 1 dominant pole and 2 non-dominant pole, and also we have a 2 0 here. So this equation for the second equation, the second order equation, use the dominant pole 0 approximation method. So if the omega 1 is the dominant pole, the higher pole, non-dominant pole can be written like this. This is the approximation. For the 0, it's similar. So typical Butterworth characteristic, having like a damping factor around 0.0, so that we don't have the peaking once we close the feedback. So this is the open loop transfer function, right? If you close, then you will have if you close, then you will get this kind of characteristic, right? One in the pass band you will have a flat, and in the other you will follow this kind of characteristic. This is closed. It's a closed loop characteristic. But if you have a large enough damping factor, you will have that like this. But if you don't have a enough damping factor, then you will have a peaking like this around the FU. So to avoid this peaking happen because of lack of phase margin. PM is not enough. Or damping factor is not large. Right? Then we have the peaking there. So to avoid that, so let's say 0.7, then we have to design such that the second pole frequency is 2x larger omega 1, the first non-dominant pole, and then 4x larger omega u. So here FU and 2x larger omega F1, this is 2x and 4x, let's say 2x FU, and this is F2 is, let's say this is F2, F2 and F3. F3 is what? 4x FU, like that, right? We can design like this. If you locate that non-dominant pole around here, then you will get around the 0.7 damping factor. Okay. So here we just assume that zero effect is negligible, but in fact, when you design and zero happen, that will actually affect the characteristic, but that will require more complicated analysis. But we will see this actually zero location affect the phase margin and also the damping factor. So does it actually affect the peaking? So you have to be careful about this peaking. So to do that, you have to make sure that this kind of a non-dominant pole should be placed far away from the FU, and also zero also must better to be located at the higher frequency. Okay, this is the design example. We know that FU and non-dominant pole, two non-dominant pole location there. Let's choose CD and CC approximately similar. Then what we have is that GM1 over GM2 ratio is like this, and GM3 over GM1 is what? 5 times CL over CC. So what it means is that so let's say the second stage GM must be greater than first stage, or approximately 3 times larger, and then again the GM3 it must be what? 5 times CL over CC, right? It must be the much larger, the larger ratio was required compared to the two-stage. In two-stage amplifier, the GM2 over GM1 was what? 4 times CL over CC, right? In three-stage amplifier, we get about 5 times larger CL over CC. So in this three-stage amplifier, it requires even larger current in the output stages. So if you use this kind of a compensation, then it will result in the larger current at the output. It will require a much larger current at the output. Okay. So the benefit of a three-stage is that you can get the very high DC gain, right? You get the higher DC gain by having the more stages. DC gain, right? This three-stage amplifier, does it improve the FU? Not that much, right? FU is defined by what? FU, the GM1 over CC, right? 2 pi. So when you use three-stage, in some application, if you need a very large DC gain, then you would go ahead with the three-stage amp. Okay. This is the three-stage amplifier design example. Let's say our required FU is 50 megahertz for the load capacitance of the 2 picofarad. So let's find the current level and CC and CD. So if you choose the CC and CD approximately same, but half of the CL, then the overall GM1 would be what? So by FU, GM1 over 2 pi CC, we can calculate the required GM1 since we know the CC and FU. So GM1 is 350 microsiemens. So current level is approximately 1/10 of that GM1 because we assume that GM efficiency, GM over ID, approximately 10, right? So assume. Now the non-dominant pole, first non-dominant pole must be 3 times larger, at least 3 times larger than 50 megahertz. So that would be 150. So that would be by the GM2 over 2 pi CD, right? By using that, we can calculate the required the second stage GM 945 microsiemens and each current level. Now the last non-dominant pole, we want that to be 5 times here FU, 5 times FU. That would be 250 megahertz. So GM3, third stage GM would be what? 3000, almost 3000 microsiemens. The current level becomes 300, more than 300 microamp. If you look at the current consumption starting from first and second and third stage, right? You're getting larger and larger and larger, right? So power consumption goes up as we have a larger and larger cascading amplifier is used, then you get the larger power is required. Okay. So this is a highlight of the power comparison. So single stage amp was 62, total current level was 62, but the two stage was total current was what? The 314, and the 3-stage amp we get the 567. So this is the example of a differential amplifier stage. So you get the output is a single-ended output, so we count that the last stage is a 1x IGM, but in here differential pair, diff pair is used, then we get the 2x larger, right? And also 3-stage become the 2x larger. First and second larger, right? By differential structure. So if you compare the current level from single stage implementation, second stage and third stage, 3-stage implementation, you can see that obviously almost here 5 times and here the almost 10 times larger, right? You can see how quickly required current is getting larger, even for the same GBW, even to achieve the same GBW, right? So FU. Only difference is that DC gain, right? By having first stage, second stage, and three stage, right? This is what you have, right? Out of cascading multiple stages. Okay.